All right. Hey everyone. We're gonna just continue with the second video of kernel exploitation. I just published another blog post on, again, HEVD exploitation. Today we're gonna just talk about write, what, where. If you already watched it already, as you remember, in the previous video we talked about how to set up the environment and also how to do a simple Stack Overflow on a kernel exploitation. So today we're going to cover what, write, what, where, and I'm going to go through my blog post to make sure that we cover the theory, and there's a lot of little code snippets that we need to add, and we need to do some source code review. So I thought that maybe it's a good idea to go through the blog post, but I already explained everything so you can go back and refer to. So let's see what we have in here. So if you remember in the previous video, if you watched it already, we exploited a kernel exploitation with a buffer with a Stack Overflow vulnerability. So what we did there was we put our shellcode in a allocated memory in user land and we executed in kernel land. So with the arbitrary overwrite, we're going to be able to write our value to pointed by what to the memory location for reference by where. So we're going to be able to write anywhere that we want. Any shellcode that we want. So, but how are we going to exploit it when it comes to kernel land? Because it's pretty different than user land. So we're going to discover different Windows APIs that we can use for our goal. For our strategy during this exploitation, there's the initial phase. So we're going to go through the source code. We're assuming that this is like a white box approach. We have the source code, we're reviewing it, and we're finding the vulnerability. So this is like taking it easy. If in the real life scenario, we would be reviewing the source, we would not be able to review the source code, but we would be able to, we'll be disassembling the binary and decompiling the code ourselves. Then, as always, we're going to find IOCTL. This is very generic for every single HEVD scenario that I'm going to cover in these videos, in this kernel exploitation series. And then we're going to verify the vulnerability with a very simple initial script. I'm going to go through the script. I'm going to explain how I'm creating these code snippets that will come in a second. And when we verify the vulnerability, get a blue screen, we're going to get into exploitation phase for the specific vulnerability, which is write, what, where. So for that, I'm going to give a bit of theory, but there are amazing blog posts out there that can actually explain why do we use these Windows APIs specifically. For the sake of the simplicity of this blog post and also for the video, I am assuming that you already go through these and read all the documentation. On Microsoft website as well, there are Windows API documentation that will explain why we're going through these API calls. So for the exploitation phase, there are a few steps that we need to do. Probably that seems like completely out of the picture right now, like enumerating all drivers. What's going on here? Like I said, we're going to come in there in a second. I'm going to repeat this later in the blog post. I'm just giving it here to see the big picture, because when you go through the blog post, then it will be very confusing. All right, so let's start with the initial phase, which starts with source code review. So we have two source code files for the specific vulnerability: arbitrary write H, which is the header file, and arbitrary write C, which is the C code. So if you go there on the GitHub repository, you can also go through yourself. So let's see what it looks like in the arbitrary write H, the header file. So in here, I put a screenshot. Let me make it full screen to make it easier. So in the first snippet you're seeing here, type def is used, which is basically used for creating new data type, which we're going to create for what and where. And if you see it in here in this line, write, what, where, that's basically an alias used in here to reference the struct, this underscore write, what, where. And then there's a pointer, you're seeing it here. It's like an alias pointer to the struct underscore write, what, where. If you scroll down a bit and there's second snippet in the same header file, we're seeing a variable here, user write, what, where. And the data type is p write, what, where, which is already defined in here, which is a pointer to the write, what, where, reference to the struct. So it's basically, so user write, what, where the data type this, it's a pointer to the struct write what where, which contains what and where pointers. So the header is just basically initializing or defining these structures and variables. And then if you look at the C code, we're going to see the vulnerable and the secure code. That's the cool thing about this driver. Kudos to the author. It basically shows in every single vulnerable scenario, how can you actually remediate this vulnerability? How could I write the code in a way that it's not vulnerable? So since we get some insights from the header file, so we're right now looking at the C code. If you scroll down in the code, first it shows like the secure code. I'm not showing it in my blog post, but I'm showing like the vulnerable version. And the secure code, it's normally checking the variables for what and where. Okay, I skipped a bit. Okay, let me go back. At the beginning of this file, it first of all initializes two variables, what and where, that's been defined already in the header file, if you remember here. So it initializes as null, and after that, it gives like the vulnerable version. So why is this vulnerable? Because normally in the secure version, it verifies if the values for where and what, if they reside in user mode. If not, this leads to kernel exploitation, as we are going to do in the next minutes. In the vulnerable version here in this else snippet, we see that there's no verification done if these are residing in, if the value to these are residing in user mode. So we know that there's a vulnerability in here that we can exploit. So the next thing we're gonna find the IOCTL code. That's the first thing we're gonna do. I'm gonna show it in a second, and IDA as well. I'm just gonna go through the blog post now, and I will I will go to IDA in a second. So if you remember from the previous IOCTL that we done in Stack Overflow, so that's the IOCTL on the top, and we're doing like jump 0 statements in here. So in order to reach out here, which basically triggers the write what where vulnerability, we're gonna check like when you subtract some value, subtract 4 from some value, if this is 0, then do the jump. And this is done 2 times. So since we are doing subtract in the reverse order, what I'm saying is from this value that we have in the top, we need to add 8 bytes to this value to make sure that we are having 0 at the end of it. So we're adding 8 bytes to this, which would end up with B. So we're getting this value as IOCTL. It's pretty straightforward. You will see that it's pretty different than the first version. When you're doing it for the first time, IOCTL, what does it mean? Everything is so confused. So it changes now. It's just part of the process now. How does it look like in IDA? I again loaded the driver. I go to functions, IRP device, IOCTL handle. If you remember, let's go to the text view. It's easy to see. So if you remember, that was the IOCTL for Stack Overflow. And let's see which function is going to be for arbitrary override, which is this one. So if you look at these functions and which one is triggering arbitrary override, it's this one. So what we're going to do is, in order from here to here, there are 2 jump 0 statements, and as I explained in a blog post, it's going to be 2 times 4 bytes, a total of 8 bytes added to this value in order to reach out to IOCTL for arbitrary overrides. So after that, we have the IOCTL code, and let me zoom it a bit. I'm going to share this also in my GitHub repository, but for now I'm just sharing on my blog post because I want to do it on bulk. So what are we doing in here? We are just using some import. This is, I'm using Python, maybe you're using C, so that may differ then. So we're using some of the some DLLs in here, kernel 32, NTDLL, PSAPI. It's not required for the initial script, but later we will need these for various API codes, Windows API codes that we're going to use. So as always, we're using create file A to create the handle. The Windows API function, if you remember from the previous video, we're doing some error handling. We're just basically adding this buffer variable for A and B, for what and where. We're going to check in Windows Debugger later to see if we are writing these values as it's supposed to, and we are writing the IOCTL code as well. Okay, I need to update this. It's supposed to be B. So let's verify the vulnerability on my environment. I did not update anything. It's the exact same thing as you've seen in the last video. And so we will just proceed with the exploitation phase. So if you remember from the beginning of this video, I mentioned the exploitation phase is going to be like that. It will have a few steps. So before we reach out to that point, let me just give a bit of theory. Like I said, there are so many good blog posts out there that basically created this series of like kernel exploitation research. So I'm just a newbie on this path, so I'm not giving a lot of theory here. I'm just trying to include like the Windows API documentation, because that's what I'm doing, going through these documentations to understand why are we using this. So yeah, I'm just trying to give like a big picture here. So let's see. So why are we gonna go through these processes? Every single step. So since there's an arbitrary overwrite vulnerability exists, we already seen this, we exploited it. So what we need to do is we need to find a way to execute user mode shellcode that we're gonna have from kernel mode. And how are we gonna do it to exploit arbitrary override? So one option to do is hull dispatch table, which is basically part of kernel, the kernel, and it's for hardware and machine instructions. So you can definitely go and check out what does it mean. But this is the technique that we're going to use to exploit arbitrary overrides. So just something to add to make you more understand. Hull dispatch table basically helps making different hardware architectures to be compatible with Windows API, Windows, instead of having different OS installed. So to this goal, we're going to use different API calls. You will see that's why we included different DLLs in the beginning, because they need different kernel DLLs for these Windows APIs. So what we're going to do is for every single goal that's been written here until this ends, we will create like little code snippets for every single one of them. It's very straightforward. I'm just going to use Python to do it. It's very logical. I'm sure you will keep it up. So to enumerate all the drivers, that's our first task, because from there we will find the address of this, which will be basically triggered with another API function to trigger our shellcode. But before we go there, first of all, we need to enumerate all the drivers to find their addresses. So we're going to use enum device drivers API call. You can check like the documentation from Microsoft. As you can see in here, it takes like three parameters, and I explained also here, it's just a documentation description that's been given in here, just put it in here to have it in one place. So the first one is this, which is basically an array that receives a list of load addresses for the device drivers. Then CB, the size of LP image array, and this is the number of bytes returned in array. So a very little code snippets that I included in here. It's basically the same API function that I filled with the values for every single parameters. And again, error handling I'm doing. And then from all these enumerated drivers, we're going to find the address for this exe. Again, we're going to use get device driver base name A API call. From there, again, you can visit Microsoft's documentation. It gets stream parameters again, and we are gonna fill it in here, as you can see it in here. Again, an error handling, and we're gonna check for the word starts with NT kernel from the current list. Once we find the address for NTOS kernel exe, we're gonna load it into load library XA. Like I said, I'm not giving like the history of why are we going through these steps. I am leaving this to you guys as an exercise. I'm assuming that you already went through that. That's the beauty of kernel exploitation. You need to understand a lot of theory. You need to understand the practice of it. But none of this is easy, so I'm assuming you already went through that. So yeah, if there are questions like this at the end of the video, why you're not explaining why you're going through these steps, I'm leaving these as an exercise to you. Yeah, it's a painful process for all of us. So again, we're gonna use load library XA function, Windows API call. Again, it takes 3 parameters. If you see it in here, current name that's been defined in the previous code snippet for finding the address of this exit. So we're just gonna fill this API call parameters according to that, and error handling, like I said, very simple code snippets. We're using different API calls for every single one of them, and doing error handling. It's like the same logic for every single little step. And after that, it's basically like a chained steps for each of them, and we're gonna find how dispatch table address. And for that, we're going to use this API function, Windows API function get proc address, to find the address of HAL dispatch table. So it just gets 2 parameter, H module and LP proc name. As you can see it in here, LP proc name will be HAL dispatch table, and this is a kernel handle coming from, again, the previous code snippet to load the XA in the load library XA. Again, I gave some descriptions in here in the source code as well. You can check my GitHub repository for it or the blog post. Okay, I'm just switching back to OneNote because it's much easier to see it in here than blog post in the video. So, all right, let's see. Okay, let's make it as big as possible. So in the beginning, in the script, we're adding the DLLs for the Windows API, obviously. Kernel 32, NTDLL, and PS API is all we need for the APIs that we're going to use in the script. And then we're going to define what and where structures, which is the new addition that we had for final script. So that I will use these structures basically in the at the end of the script to trigger the vulnerability. I'm going to add the shellcode. It's the same one that I use in the Stack Overflow exploit, so you don't have to like recreate this at least. This is the same. And of course, we're going to defeating the DEP bypass basically with virtual log. We're going to create the RWX memory, and we're going to copy our shellcode in that region to bypass DEP. And then the steps are exactly how I defined in the previous code snippets. These 4 steps, nothing different. I'm just skipping to that part quickly. Same code snippets. And then we're going to trigger the exploit in here. So what are we doing is we are writing the variable of write what where with the function write what where as we defined in the beginning in here with that structures. So it's going to take, okay, then write what where's what would be payload final variable. This is going to be the final shellcode. So this is what would be shellcode, and the where would be HEL plus 4 bytes as we discussed in the beginning. And then the pointer would be just like putting this in a pointer, the same thing, right, what where. And we're going to print where the location of what and where is. And after that, create file A to create the handle and device IO control with the IOCTL. The same thing that we've done in the previous exploit, nothing different. Besides the IOCTL, it was like the same with the 3 at the end, and this is changing to B now. And the only other difference that I'm doing is if you go through the theory, you're going to know that this API call is the one that's going to trigger the exploit, that's going to call the where location, which is basically HEL plus 0x4, and execute what, which is our shellcode. So we need to make sure that this is added, because without that, the shellcode, this is the only reason that the shellcode is working basically. So we need to add that. I think I didn't include like the API call URL, but you can easily find it. Just Google it quickly and pop the shell. The same thing that I use in Stack Overflow. So I'm just gonna go back to my virtual machines. And I'm gonna go there and I'm gonna run the script to just show you that it's working. Okay, so I'm gonna run this. I can't believe that I did not add the environmental variables for these virtual machines. I needed to recreate them for these videos, so that's what I'll be continuing to write the full pad like that. So and here we go. We got another shell as if you ask for my and the other the system. So that's the final exploit that's working. But yeah, there are a lot of videos that I'm gonna create. There are some of the topics that I did not finish yet, but most of them I did for OSE preparation. Hopefully it helps you guys. Otherwise, I think I just like put it out there. What I've been working on since like over a year. There are like few missions that few videos that I'm gonna create for vulnerable driver HEVD, and after that there are some bypass videos that I'm gonna go through, and then there are some browser exploitation as well, guest host escape. There are a lot of things I want to create videos of, but yeah, hopefully I can find time and energy to create them all. And hopefully you'll like the videos and learn from it. So see you until the next video. Cheers, guys.